okay, differential equations. We've got the size n of a population of a small island, and it says could be modeled as a continuous variable. And then it says at time t, right, the rate of increase of n. Now, important here, the rate of increase. Basically, we're looking at how n increases, but the rate of it, when you see that word rate, we've got to think of the derivative, okay, right? Because the derivative, right, differentiation refers to the gradient, doesn't it? Yeah. And that's where we'll get then the rate of increase by looking at the gradient, the steepness of it, okay? So rate of increase of n is talking about how n increases over time. So we would differentiate it, okay, and that's looking then at the gradient, isn't it, of this graph, if you like, n, where n represents the population. And the gradient of it looks at how it's increasing, right? And it is increasing, right? So that means it's obviously positive, right? It's a positive gradient because it's increasing. Okay, so the n is increasing, so it's going to be positive gradient. And it's saying it's directly proportional to the value of n. Okay, so when we see that word proportional, we've got to think back to GCSE, and we use that sort of fish symbol, the alpha symbol, yeah, to show it's proportional to the value of n. Okay, so that's key there. Now in part A, it says write down the differential equation satisfied by n. Now we've written this here to show the proportionality, but in order to get a differential equation, I need to have an equal sign in there, yeah? Because if you remember with equation's got an equal sign in it. So again, back to GCSE, right? When something's proportional, okay, you can get an equal sign in there so long as you introduce a constant k to represent, right? This constant k, like we had at GCSE, represents this proportionality, okay? The constant of proportionality, okay? So that we can say that, look, dn dt is some constant multiplied by n, right? Because it's growing at this particular rate, right? And we'll work out k now, okay? We'll work out k. But we've got essentially part A answered, right? That's our 1 mark here, okay? Already achieved. Part B then, it says show that n equals ae to the power kt, where a and k are constants, okay? So what I'm going to do now is, right, I need to integrate, right? Because this is the derivative of n, isn't it, okay? It's the gradient, isn't it? It's gradient function. I don't want the gradient function. I want the actual curve, if you like. I want the actual n function. So I'm going to integrate. But when I integrate, I've got to be careful because I've got n's on both sides, haven't I? Yeah, I've got n here, but I've also got n there. So what we say is we separate the variables. So what I'm going to do is, I've got k times n here. I'm going to keep the k where it is, timesing by n. I'm going to keep the k there, but that n I'm going to take over the other side. Because I'm like timesing here, if I take it over, I'll have divide by n, yeah? Okay. And the dt, you might be wondering where it's gone. Well, I'm going to take the dt over to the other side. So I've got k here, put dt there. Okay, so I've separated the variables, got the n's on one side and, you know, the t's on the other side. Okay, and of course separate the variables means that I'm going to integrate. Okay, and I can work out then the integral of each of these. Now remember now, dn over n, right, the way I've written that is the same as 1 over n, right? dn. Okay, you know, you can write it like that. You can put the dn there if you want to, so if they're multiplying together, you've got that. But if you prefer to see it written like that, it's not a problem. But 1 over n, if you think about it, when you integrate it, it'll be ln n, yeah? That's what it'll be ln n. And that will equal to then k. Now when you integrate it, remember k is just a constant, okay? So we could even, with that one, we could have even taken it outside of the integral. And we could have just had 1 then dt, yeah? Because that's what it would be if you take it outside. It's a constant. If you integrate 1, then it just becomes t, doesn't it? So, you know, that becomes t when you integrate it, and you've got k there next to it. So you've got kt, basically, okay, kt integrated there. And of course, don't forget, then you've got your plus c, okay, your constant of integration. Now, what I'm going to do now is they want it in this form, right, ae to the power kt. So what I do then is, right, because I want to get n, right, because I want to get n, I'm gonna take the ln over the other side. You can think of it like that, right? And if I take the ln over the other side, of course I've got to do the opposite. I've got to do the inverse, so I've got to do e the other side, right? So I've got to e all of this. So e to kt plus c, all right? And what you appreciate then is, when you've got these powers added, right, just rules of indices, this would be the same, wouldn't it, as e to the kt times e to the c, wouldn't it, yeah? So when you're adding powers, it's the same as multiplying the terms, you know, put these back together, couldn't I? And I get that there. And you need to appreciate then, well, if c is a constant, e to the c is a constant. So we can say, look, let e to the c equals to a. Right? Instead of writing e to the c, we can write a, which is a constant. And we get then exactly what they want. Okay, they wanted this, didn't they? They wanted us to say that this is equal to n e to the kt. Okay, so we've got our part A and part B sorted.